Okay, Assalamualaikum and very good afternoon. Okay, now we look into the chapter number three, the kinetics of a particle. Here we look into the work and energy. Okay, on this particular chapter, we have five sub-chapters where we start with the introduction of the kinetic energy, followed by the work of force, the work of a couple moment, principle of work and energy, and the final one is the conservation of energy. Okay, on the first one, kinetic energy, as what you have learned before in your high school. I think you have been introduced to this kinetic energy. Kinetic energy is the energy that object possess due to their motion. Okay, so Ke, or the kinetic energy, is equal to one half times the mass m times the velocity of that particular mass. Okay, because for kinetic energy, the mass or the system must have some motion. Okay, and the kinetic energy we measure in joule. Okay, on the right hand side here, what we can see, there is a young boy, okay, riding a bicycle, going up a hill, okay, climbing up. During the climbing, he deal with some kinetic energy, and when he stop or at the very top of the hill, what he actually have the highest potential energy at this particular point. Then going down this particular hill, he, he also gain a little bit of kinetic energy. Uh, the same thing here when there is a, a girl, okay, throwing a ball at a certain height here, then you can see that the potential energy being transformed into the kinetic energy. The ball fall down. Okay, moving on to the real stuff. Okay, the kinetic energy of the entire body is determined by writing similar expression for each particle of the body and integrating the results as shown here. This particular equation may also be expressed in terms of the velocity of a point. Okay, imagine that down here you have a point. Okay, if the body has an angular velocity omega, okay, this is the whole body, the blue color here. Okay, and this is the omega, the rotation. Okay? Then then we have vi is equal to vp plus vi with respect to p. Okay, vi is equal to vp plus vi with respect to p, this one, and you can expand it like so. Okay, the square of the magnitude of vi is thus, okay, this one. You know that for the kinetic energy, v is square, so vi times vi or vi square, you can expand it like so. Okay, and this one, because over here, this is your vi, this is the component, because vi have a component in the I and also in the j direction, because we are looking at the two-dimensional problem here. So that's why you have a two component. Okay, you square, then square on the second part. Then you further expand it, and then you get something like this. Okay, substituting this into the equation of kinetic energy, Okay, substitute into this. Okay, this part here, the long equation here, you put it here, then you do the integration of m, okay, with respect to each individual component here, then you will arrive with this expression down here. Okay, the first integral on the right represent the entire mass of the body, since y bar m is equal to uh, integration of y dm, and x bar m is equal to integration of x dm. Okay, this one. This is x dm, and this is the y dm. Okay, but means that the first integral is this part here. Okay, this represent the mass of the body, and this one is for this, and the third part here for this one. And the last integral, the last one here, represent the body moment of inertia. Compute about the z-axis passing through point P. Okay, and thus you will have this equation when you do this math up here. Okay, as a special case, okay, as a special case, okay, looking at this equation up here as a special case, if point P coincide with the mass center of the body, okay, for any object or any particle uh, with mass, of course, then that particular body or mass will have their uh, uh, what we call center of gravity or center of mass. Okay, okay. If that is the case, then y bar is equal to x bar is equal to 0, which means that the distance from the origin, from the center mass, is 0 because it is coincide. Okay, that particular position is coincide with the center of mass. So that's why this the second and the third term here is equal to 0, because y bar equal to 0 and x bar equal to 0. Then what we have is we have this, the first part here, okay, you can see down here, and the last one here, you can see down here as well. Okay. Okay, both terms on the right side are always positive since Vg and omega are squared. The first term represents the translational kinetic energy reference from the mass center, and the second term represents the body's rotational kinetic energy about the mass center. Okay, moving on. When we want to look into this kinetic energy of a dynamics problem of the kinetic energy, then that you will need to evaluate each of it and see whether it lies or it's what the body is actually doing at that particular time, whether it is just a translation. Translation means it just move uh, from point A to point B. Okay, more or less that is the definition for translation. Okay, and rotation about a fixed axis uh, like uh, a rotating wheel. Okay, bicycle tire. Okay, if you sorry, not a bicycle tire, because that is involved with general plane motion. Bicycle tire is a under general plane motion because as the wheel, okay, tire or wheel of that particular bicycle is rotating, the bicycle itself, the whole bicycle itself is moving. Okay, so that's why you will have the translation and the rotation together. Okay, rotation means it just rotate like down here. This lever here is rotating on this fixed point O. Okay. Okay, moving on to the second subtopic. Okay, what we have here is the work of a force. Okay, the work of a force. So work is equal to the force time distance. Okay, work is equal to force time distance. Uh, we the unit that we are looking at is Newton meter or foot pound. Okay, it depends on whether you use SI unit or other units. Okay, first one, work of a variable force. Okay, if an external force F, okay, this F here, acts on a body, the work done by the force when the body move along the path S. Okay, this is the F, and it is a path S. Is denotes like this, and theta here is this one. Okay, so the work done U, normally we use a U because some other books they prefer to use different symbol. Okay, so uh, here what we have is we use a U, and F is the force, represent the force, subscript F. So you integrate F respect to the dr. Dr is the small component of uh, when this particle is moving. Cos theta is given here. Okay. Okay. Work of a constant force. If an external force acts on a body and maintain a constant magnitude and constant direction while the body undergoes a translation, then the above equation can be integrated so that the work become, okay, become like this lah. Okay, this is the equation. Okay, the difference between on the left we have a variable force, on the right we have a constant force. Variable force because of the this, if you look carefully here, it move the path S here is not linear, not straight line. So you have to do it. Uh, you need do it numerically. So you need do it at to prevent large errors. For example, then you have to do it at a smaller. Uh, you basically you can if let's say there is point A and there is point B, then you have to uh, uh, split, or you have to uh, yeah, you have to split this path into several small elements so that you can evaluate the whole the work done on this part. Okay, unlike this one, you have a straight line, then it is pretty much straightforward. Okay. Okay, work of a weight. The weight of a body under body does work only when the body's center of mass undergoes a vertical displacement. If this displacement is upward, okay, the work is negative. since the weight is opposing to the displacement. Okay, if you want to consider this particular case, okay, it is being defined the orientation, then the work is negative. If the displacement is upward, then the work is negative. So this is according to this figure here. Okay, if a linear elastic spring is attached to a body, okay, like what we have down here, the spring force acting on the body does work when the spring either stretch or compressed. Stretch means you pull it, okay? The spring become longer, and when you compress, it become shorter from to a further position. In both cases, the work will be negative since the displacement of the body is in the opposite direction to the force. Okay, this is the question that you might be looking later. Okay, force that do not that force that do no work. Okay, no work done. Okay, there are some external force. This force is actually it's act either at fixed point on the body or they have a direction perpendicular to their displacement. Example include the reaction at the pin support about which a body rotates, the normal reaction acting on a body that move along a fixed surface, and the weight of the body when the center of gravity of the body move in the horizontal plane, like what we have on the left here. Okay, a frictional force Ff given here acting on the round body as it rolls without slipping over a rough surface also does no work. Okay, it is because during any instant of time, okay, instant of time we denote it as dt, the friction force, okay, or F subscript F acts at a point on the body which has zero velocity. Okay, we are talking about the instantaneous center IC. And so the work done by the force on the point is zero. In other words, the point is not displaced in the direction of the force during this instant, since the friction force contact successive points for only an instant. The work of Ff will be zero. Okay. Now, the third sub topic where we look into the work of a couple moment, where we have a force and we are dealing also with a distance. What is moment? Moment is a force time the moment arm or the length r, normally what we referring here. Okay, consider the body on this figure. Up here we have A, B, and C. Okay, first one, we look at the first one, which is subjected to a couple moment M, which is equal to the force time R. Okay, force time R. If the body undergoes a differential displacement, then the work done by the couple forces can be found by considering the displacement as the sum of of a separate translation plus rotation when the body translates. The work of each force is produced only by the component of displacement along the line of action of the force. Okay? Clearly, the positive work of one force cancels the negative work on the other. When the body undergoes a differential rotation d theta about the arbitrary point O, okay, this one, okay, then each force undergoes a displacement. Okay, like so, in the direction of the force. Hence, the total work done is here on the right hand side. Okay. Okay. Let's look into one particular example here. Okay, with this figure down here. Okay, the bar shown figure below has a mass of 10 kg and is subjected to a couple moment of m equal to 50 Newton meter. Okay, the unit for moment, remember, it is a Newton meter. For force, it's just a Newton. Okay, so this particular bar is subjected to a couple moment of 50 Newton meter and a force P of 80 Newton. Okay, at the end of this bar, which is always applied perpendicular to the end of the bar. Also, the spring has an unstretched length of 0.5 meter. Okay, the unstretched length of the spring is 0.5 meter and remain in the vertical position due to the roller guide at B. Okay, here there is a roller guide. Determine the total work done by all the forces acting on the bar when it has rotated downwards from theta equal to 0, which means that initially this particular bar is horizontal. Okay, this particular bar here is horizontal, and at that particular position, the spring is yeah, the bar here is horizontal. Okay, and it is being pushed by this force until it is become vertical 90 degrees. Okay, okay. We look into the weight first. Okay, since the weight is equal to mass time the gravity, that we got our weight. Sorry, yeah, we got our weight of 98.1 Newton, displaced downward 1.5 meter. Okay, you can refer to this particular diagram here. Why it is displaced 1.5 meter, you can see that for this particular bar, the center of mass is in the middle. So because it is a uniform body, then the center of mass is at the center of it. Okay, and we know that the total length is 3 meter. Then from the center of mass to this pivot point, or here is 1.5 meter. So that's why we have a 1.5 meter. Then the work is, yeah, you have the weight, this one, times by the 1.5 meter. So this is, okay, why it is the work is positive. Okay, I hope you got the answer. Couple moment, the couple moment rotates through an angle of theta equal to pi over 2 radian. Why pi over 2? You know, like for a complete circle 360 degrees, that is equal to 2 pi. Okay, 2 times pi. So how about pi? Pi is equal to 180 degrees. Okay, then pi over 2 is equal to 90 degrees, because we know that we are looking from theta equal to 0 to theta equal to 90 degree. So 90 degree is equal to pi over 2. Okay, this is theta equal to pi. Hence, we know that due to the moment, okay, moment, you need to multiply by the angle of this rotation. Okay, you got this. Then the last one, where you have a spring, okay, that resists the motion. Okay, when theta equal to 0, at the initial point, the spring is stretched. Okay, if you refer to this diagram, okay, it is shown that it is 0.75, and it is mentioned that the spring has unstretched length, which means that um the spring, if the length of the spring is more than this, means that there is a force involved. Okay, so you need to get the difference of this length, which is equal to 0.25 meter. And when theta equal to 90 degrees, the stretch is 2 meter plus 0.75. Okay. Why? You know that from this point A to the point where the spring is attached is 2 meter. Okay. When theta equal to 90 degrees, theta equal to 90 degrees means this particular bar is straight. Okay. Vertical. When that happens, this particular point will be somewhere here. Okay, will be here. And this particular position, if you measure from this point, it is 2 meter plus 0.75. Okay, and of course, you plus the 0.75, but remember that the unstretched length is 0.5, so you have to minus that one. So it becomes 2.25 meter. Then you just plug in all the values to calculate uh, the the energy due to the spring force, like so. Okay, half of 30 Newton meter, because 30 Newton meter is given. It is the constant for this spring. Okay, and 2.25 is this one. Okay, basically you need to calculate when theta equal to 90 degree. This is when theta equal to 90 degree, and on the second part here, when theta equal to 0 degree. Okay, when theta equal to 0 degree, you have a displacement or x, which is equal to 0.25, and this is your answer. Why it is negative? Because you see that this is pointing upwards, so then this is the case. By inspection, the spring does negative work on the bars in x in the opposite direction to the displacement. Okay, so it is like that. So as the bar moves downwards, the force is displaced through a distance of pi over 2 times 3 meter. Okay, due to the force. Okay, then this is the calculation of it. Okay, the total work. Okay, at pin reaction, the force in AX and AY do no work since they are not displaced, because this particular point is just stay there. Okay, that it didn't go left or right, up or down, so just stay static over there. It just rotate, so no the reaction force is not considered in this case. Then total work, the work of all the forces when the bar is displaced is like so. So you have to first take this one, that is equal due to the weight. Okay, up here. Then 78.5 is from the moment. And this one due to the spring. And the last part here is due to the force P. Okay. So basically, there are four items that you have to take into account to solve this particular problem. One is the mass of this particular uh, object itself. Then you look into the external forces or moment acting on the object. Okay? Where first you have the moment, spring, and also external force P. Okay. Okay. Moving on to the principle of work and energy, 3.4, where the principle of work energy, the principle of work and energy, or work energy principle. Okay, work done is equal to change in the kinetic energy plus change in potential energy. Okay, this is one of example. Okay, from the principle of work and energy, the principle of work energy for rigid body can be shown like so. This equation states that the body initial translational and rotational kinetic energy plus the work done by the external force and couple moment acting on the body as the body moves from its initial to its final position is equal to the body final translational and rotational kinetic energy. Note that the work of the body's internal forces does not have to be considered. Okay, the internal forces does not have to be considered. These forces occur in equal but opposite collinear pair, so that when the body moves, the work of one force cancels that of its counterparts. Furthermore, since the body is rigid, no relative movement between these forces occur, so that no internal work is done. This is one of the assumption. Okay, when several rigid bodies are being connected, they're connected by inextensible cables or in match with one another, the above equation can be applied to the entire system of connected bodies. In all these cases, the internal forces which hold the various members together do no work, okay, no work, and hence are eliminated from the analysis. This is the procedure to solve problems related to the uh, that involve velocity, force, and displacement. Okay, for the kinetic energy. Okay, moving on to the next example, where down here we can see that we have a 30 kg of disc. This is the disc. The weight of this particular disc is 30 kg, and it is pinned at point O here. Okay, it is pinned here, and on this particular problem, you need to determine the angle through which it must rotate to attain, okay, to attain or to get an angular velocity of 2 radian per second starting from rest. It is acted upon by a constant couple moment m, which is equal to 5 Newton meter. The spring is originally unstretched and it caught warps around the rim of the disc. This wrap around the disc. Okay, so you can see that the spring constant is 10 Newton meter and has a couple moment acting on this particular disc. Clockwise direction, 5 Newton meter. Okay, so now this is this because the first thing first is you need to draw your uh, free body diagram. Okay, this is the free body diagram to to show what are the forces involved. Like here, that this is due to the spring. Okay, due to the spring, because the spring resists the motion. So that's why the direction is downwards. And on this particular pin point here, point O, then you will have a reaction force OX and OY. Okay, and the wheel itself weighs 30 kg. Then 30 kg you need multiply by the gravity, then you get the weight of this particular disc is 294.3 Newton. And note that this particular disc is subjected with a moment of 5 Newton meter. So, okay, now what we need to do is we need to solve when the it is when the T1, okay, at the initial uh, uh, yeah, at the initial point. Oh, sorry, not initial point. Uh, because it's starting from rest, so that T1 is equal to 0. Then when is this particular moment is start to give something, then this particular disc will move, will rotate. Then you have this kinetic energy due to the rotation. Okay, IO here is the mass moment of inertia of this particular disc. Okay, it is equal to half m uh, r square. Okay, given r is equal to 0.2 meter, so square here and multiply by the omega 2, which is uh, given here 2 radian per second. So you just calculate this one. Okay. Then from the principle of work and energy, you can look into this. Okay. This is before, this is after. So before, what we have is the this part here, up here. Okay. At rest, so T1 is actually will become 0. Then we have something here. What is this? Is m theta is the moment acting on this particular disc. Okay, times with the how much angle that this particular disc rotates. Okay, just put theta, and then on this the second part here, what we have is the due to this Fs, the spring force. Okay, the Fs is equal to half minus half kx square. So just plug in the values. Okay. Then everything on the left is clear now. Then you will just put this T2. Okay. After these things happen, then you already calculate up here. Okay, that is equal to 1.2 joule. Okay, due to this rotation. Okay, just imagine that on the left hand side, okay, from the principle of work and energy, in simple way, how to understand this particular problem is on the left is what you give. Okay, what you give to the system. Then on the right hand side is what you get after the system is given the moment and forces. Okay, so there is a before and after. So then there is the what it means by the subscript 1 and subscript 2. Okay, to get the general understanding of what is going on here. Then you just do the math. Okay, not very difficult. Then you can solve this quadratic equation like so, and you get theta equal to 13.9. Okay, some of you might notice that how why it is like this. Okay, this is the circumference. Circumference. Okay, the next example is given here. Okay, um, I hope you can go through this particular example in your own. Okay, or we can discuss that in the class. Okay, conservation of energy. We look into the law of conservation of energy. You must know that energy cannot be created or destroyed. Okay, it can only transform from one into another. Okay, from one form into another form. Okay, okay. When a force system acting on a rigid body consists only of conservative forces, the conservation of energy theorem can be used to solve a problem that otherwise would be solved using the principle of work and energy. This theorem is often easier to apply since the work of a conservative force is independent of the path and depends only on the initial and final position of the body. Okay. Here what we have is the gravitational potential energy down here. Okay, of course you will look into the datum. What is datum? Datum is a reference point. Okay, like in this case, this is your zero or your ground level. Okay, that is in general that is the definition of it. Okay, elastic potential. We also have elastic potential energy. Okay, like the spring. Okay, uh, then we have the conservation of energy. Okay, it is like so. In general, if a body is subjected to both gravitational and elastic forces. So the first term here is the gravitational, and the second part here is the elastic forces, V due to the elastic forces. Okay, realizing that the conservative forces can be written as a difference in their potential energies. Okay, conservation like this. Then we can rewrite the principle of work and energy for a rigid body as like so. Okay, T represent the kinetic energy and V is the potential energy. And on this part here, that could be the friction force or other form that also can be we can say that is the non-conservative forces. Here, these non-conservative forces represent the work of the non-conservative, such as friction. Okay. Okay, if you neglect the friction, then everything will be like so. Okay, if you ignore the friction force, then it will be like this. Okay, there is one particular example. Okay, where we have a spring and we have like a rod or like a piston here. Okay, rod A B. Okay, and this at A and at B we have something. Okay, so at B, this particular uh, let's call it a piston at B here, it move in the vertical direction, and at A it move in the horizontal direction. So, and on this particular problem, you need to determine the angular velocity of AB when theta equal to 0. Okay. If the rod is released from rest when theta equal to 30 degrees. Okay, this is the process. What you need to look at is for V1 is the due to the gravity, and this one due to the kinetic, the elastic part of it. Okay, potential energy. So for S1, just the trigonometry of this particular system, then you can resolve this problem. Okay, and for the kinetic energy, just now is the potential energy of this spring as well as this gravity of this rod. Okay, then we look into the kinetic energy, the initial kinetic energy before. T1 means before. Okay, and we know that it start from rest, so it is equal to 0. If let's say the problem saying that uh, the object or the particle is moving at the speed of let's say 2 meters per second, that means T1 uh, must be something. It is not equal to 0. Okay. However, if it is mentioned that it released from rest, okay, from rest means no motion, so that is equal to 0. Okay. Then in position 2 or after, the angular velocity omega 2 and the rod mass center has a velocity of vg2. Then you need to calculate, because uh, here on this first part here, that is due to the translation, and this one due to the rotation. So this particular rod would experience um, general motion, okay? Both translation and rotation at the same time. So there is the things. So you need to use the uh, kinematics so that you can get this particular equation. Okay, T2, and from the conservation of energy, you look into the what you have before and what you have after. Okay, what you have before, the kinetic energy is because no motion involved initially. You only deal with the spring, so the potential is energy is there as we have calculated here. Okay, okay, like so. Then after the process, then the potential energy change form into the kinetic energy T2. Okay, like so. So you can get the value of omega, the rotation, the angular velocity of this rod AB. Okay, there is another example. I hope you can go through this particular example and also this one. Okay, that's all. Thank you.